This is a redox titration using iron tablets and potassium manganate. And this is essentially how you prepare your iron tablets, your sample, and everything that you need for this practical. Now, this is a very old method that I have on hand, and I'm not going to follow this 100% completely, purely because it talks about preparing potassium manganate solution, but I've already bought some. So what we're going to do instead is we're just going to prepare the iron tablets. So obviously for a titration you're going to need a burette, you're going to need a pipette, and you're going to need a volumetric flask. You're also going to need some sulfuric acid, some deionized water, and a measuring cylinder obviously. So let's get started. So first off, these are my iron tablets, straight from Asda. Okay, and it says, and you do have to take a look at the bottle. It says that per tablet there is 14.5 milligrams, which is fine. You don't want to go over anything more than 250 milligrams. Because then you're going to take up a lot of your burette volume, so much so that you may have to refill your burette. So because these are 14.4, I'm going to take 5 of these and I'm going to weigh them. I'm going to weigh them before and after. Okay, I'm going to note that down. On the pen. So iron tablets, I'm going to put times 5, and that comes out to 1.62 grams, which is what I'm expecting. Okay. And now I'm going to have to crush them up. So here I have a pestle and mortar. I'm just going to shove them all in there. Okay. And I'm going to start crushing it up. Now you need to try and get it into a fine powder, just so it, oh, these are actually quite easy to break up, really. That's good. The last time I did this, they were so hard to break up. So I'm going to try and get this into a nice fine powder. Easy. And then try and get as much of that, back into my beaker. Normally you should use a weighing boat for this, however, budget, we don't have any left, so just carefully put that back into the beaker, and I'm going to re-weigh it. The reason for that is you are going to lose some of your mass in the pestle and mortar. It might only be little, but it still counts for your calculations. Whoops. Try not to break glassware as you do this. Okay, I'm going to reweigh this. And there you go. So 1.44. Okay. Try and get as much more out as possible. Okay, 7. Alright, so now that I've got that, you now need to try and get it into a volumetric flask. 250. Okay. And there are many methods, as you see, and they do vary. This is how I do it. Okay, so whilst it's in here, I'm going to take some sulfuric acid, just a 1 molar, okay, and I'm going to measure out 50 just reading 100 milliliters of sulfuric acid. And you do need to be careful with this, obviously, because it is an acid. We want it to be as accurate as possible, so plastic pipette, just to get that last bit. Now I'm not going to pour all of this into my little beaker. And remember to read from the bottom of the meniscus, bottom of the water line, or the liquid line, whatever you want to call it. There we go. Sorry. That's my phone. Okay. So from there, you are going to want a little funnel, and we're going to dissolve some of this using our sulfuric acid. Now it's important to do this because we want to try and get our powder fully dissolved for our titration. Okay, some methods do say to heat it, some methods say to add 2 molar sulfuric acid and to leave it overnight. This is just the method that I found easiest and quick to do. Okay. So as you can see, it's starting to look very nice. Okay. And slowly I'm just going to add that into our nice clean volumetric flask. You just want to keep adding more, giving it a swirl, getting it all mixed up as much as possible. You can, if you want, get a pipette, just give it a stir around. The idea is you're using your sulfuric acid to wash the beaker. go. So I'm just going to pour the rest of this into here to wash that funnel out. Now for the rest of this, up to the water line, the line there, I'm going to use some distilled water, purified water, however you want to say, call it. And I'm just going to pop the lid on, just give it a little bit of a swirl. And as you can see, it looks to be dissolved pretty well. You still see some little bits floating around, which is absolutely normal. That's because it's the binder that's holding the tablet together. Those are little bits that you can see. Fill up my bottle again. As you get towards the neck, you're going to want to slow down because it does come up pretty quickly. So as you can see here with all these little bits, this is mostly just the binder, it's not the iron, it's the binder in the tablet. So we need to be careful as we go into the line because our water line is going to be just at the top. So this is not going to be as accurate. But we can do our best. There we go. And from this, you're going to need to invert it 20 times. So hand needs to be firmly on top and bottom, and you need to really make sure that you keep your hand on that stopper, otherwise it's just going to go everywhere. Obviously you still need to be careful because glassware is fragile, so you don't want to give it too much of a good grip, especially because that neck here is a weak point. And you don't want to top it up after. You may be tempted to. You may be tempted to top it up. Don't. Okay. Okay. And here is some pre-made potassium manganate. It's 0.02 molar. This is fresh. And as you can see when I start to pour it, it's a nice deep purple pink. There we go. So that is our iron sample all done, and this is our manganate straight from the bottle. And obviously we do need a glass pipette, and we also need a burette. All clean, all nice. Now this is an old-fashioned pipette filler, bulbous. I prefer these over these, just because you have more control, it's more accurate. And these, if you don't pick the right one up, it's not going to work. So I'm just going to clean the solution a little bit. It's important to make sure that this doesn't roll around, so stick one of the pens on and lay nice and flat, because what you don't want is this to roll and shatter on the floor. I don't need that anymore, it's fine. Put these in there. Okay. So, when you are filling your burette, you have to do it on the floor. Reason for that is you are using chemicals. Okay. You do not want acid or any base or anything like that to fall. So, for instance, I'm sorry about the angle. But what you don't want is, as you're pouring it, see? Obviously I'm not wearing a lab coat, but it can easily slide down your arm. So you're going to have to take it and put it on the floor. You're also going to want to use a funnel. Now again, there's much controversy as to what you put in into the beaker and what you put into the conical flask. I will be honest, because this is full of little bits, okay, that's going to get clogged up in your burette. Which costs more to replace, your burette or your pipette? Your pipette is going to be much cheaper. So, what I do it is, I take a sample of this and I put the manganate in my burette, just because I know that there's going to be no bits in that. Obviously I've made sure that the tap is pulled to the bottom. Now the only trouble is with this, you're not going to be able to see the bottom of the meniscus, which is fine. So long as your measurements are consistent, you can use the top of the line. Okay? I'll have a brand new pipette. And I've gone past 0 actually. So what I'm going to do is need to get air out of the bottom of the It doesn't really matter where you start from. You can start from 0 if you want. With potassium manganate, it's more difficult to see the 0 mark, so it might be better off if you just go past. Okay, and I'm going to show you how difficult it is to see the marks with potassium manganate. So my pipette is facing the front. Okay, and let me just show you up here. it is extremely hard to see the bottom of the meniscus. So in this case, you're going to do a bit of dodgy chemistry, okay, a bit of dodgy techniques, and you are going to have to read from the very top of your waterline, liquid line, whatever you want to call it. Okay, but as you can see, I've got no air bubbles. You need to make sure that your burette is nice and straight in all angles. Because what you don't want is to twatch it up. Okay. So obviously you're going to need a table. Record your results. Pardon me. Trial 1, 2, 3. End goes second. No, sorry. End goes first. Then start. Then change. That means then you just take this number from this number and you get your change. Okay. So our start is 0. That's halfway, so 6.5. Okay. And so my iron solution, I've made it up to 250 ml with 100 centimeters cubed of sulfuric acid, SO4, and water, that's distilled water. Okay. And I've put potassium manganate in the burette. Okay. Now for each of these, you trial 1, 2, 3. I'm taking a 25 centimeter sample. For Aqualot. Okay. And then we start titrating once when you've transferred your sample over to your conical flask. You may be asking, what indicator are you using? You don't use an indicator for this. It is self-indicating. What you will need is a timer. Okay. As you're adding the potassium manganate to your sample is going to turn pink, and it's going to change back relatively quickly. Your end point is when the pink stays for 30 seconds. If your pink stays for 30 seconds, that is your end point. That's when you read your end volume from your burette. Okay? Now, roughly when I've done this before, you're looking for a change of around 14 centimetres, roughly. It does depend on the type of tablets that you use. It does depend on the concentration of your manganate. It does depend on quite a few things. Okay. But that is the startup, and I'm going to do a trial run so that you can see what exactly it is that you're looking for. Okay, so I'm just going to send this over here.
Sorry, it's just me.
Okay. So, I'm going to empty my pet filler. Ooh. Holding it by the glue tip. And I'm just putting it on gently. You don't want to shove it in from here, because if you shove it in from here, it's going to break and it's going to go into your hand. Okay, you need to hold it at the top. Safety first. Never seen one of these before to use it. There's A, S and E. Okay. A is your start point, you hold it down and squeeze it to get all the air out. S sounds to suck, so you press and hold this to get it up into your pipette. And then E, which is at the side, is empty, so you press and hold that to let the air out. Okay, so make sure that doesn't hold out. Yeah. I have a 25 centimetre sample of my iron tablets, and I'm going to slowly start adding. Even though this is my trial, I do want to try and get it as accurate as possible. Okay. But as mentioned, I know from experience that roughly it should be around 13, 14. So I'm going to drop it to 10 and then see where we are at the time we're ready. That's roughly 10. It immediately changes. So now I'm just going to start adding it slowly, just so that I can swirl at the same time. Okay. So this is temperamental, that's fine. So that pink's taking longer and longer to leave. Now I'm just going to try and do a drop at a time. 10 seconds. So maybe if we have 2 or 3 drops. That's 4. Start. Okay, 15. Four. You can see it's stronger now. Okay, 20-ish. Oops. Another 4. And I've just gone past 13 now. Seconds. Okay. 4 drops again. Remember, this is just a trial, so it doesn't really matter that I'm not doing a drop at a time. This is just to get a rough idea, a more accurate idea of when I need to stop. Nope, not yet. That's annoying. So I'm just going to get that one. Can't drop. Oops. Oops, it is. Okay, that's just before 14 now, so. So this looks like it might be it. 25, 26, 30. Yep, so that pink's still there, even though it's going. That is my end point. Okay. So reading that, it's 13.90. So see, roughly, you're wanting to be between 13 and 14. That's how you know, especially for these tablets. These with 14 milligrams. Okay. Now, why is this turning back into our pale solution? Well, the reason for that is because it is a redox titration. So the reaction goes like this. So you have your iron, Fe, plus K, potassium, manganate. Oops. And that creates iron, Mn, H2O, and some technically KOH. Okay. Now what we're focusing on is these and your water. Okay. So your half equations, your Fe is being your Fe is going from a 2+ to a 3 plus. Okay, so you have lost an electron. Okay, so this has been oxidized, and your manganate, which is the MnO4 minus, is being reduced. So it takes the electrons and some of the hydrogen from the water that's in your sample, okay, plus electrons, okay, and it is reduced to Mn2 plus H2O, okay. Now we do have to balance this. Okay, so luckily this is fine, it's this. So obviously you can pause here, you can take your time to try and balance it yourself. Okay, but here is the answers. Yeah, 5. Okay. Yeah. So for our full equation, okay, we need 5 electrons to be added to our manganate. So technically this is times 5. So you will have 5 ions to 1 manganate ion. Okay. So these are the half equations reduced. When you've cancelled everything out, after you've done all your spectator ions, you should be left with 5 Fe2 plus MnO4 minus plus 8H plus goes to 5 Fe3 plus Mn2 plus 4 H2O. Okay? So this is what's happening. So for every manganate ion, there should be 5 iron 2 plus ions undergoing a oxidation and reduction. Okay? And slowly, over time, these will react back together to go back to here. Okay, so this is technically a reversible reaction as well. And our reversible arrows look like that. Yeah? So the pinkness that we can see is from this. It's from your manganate 2 plus ion that's being formed. Okay, and as it goes back to clear, it's forming back into manganese ion. This is manganate. There we go. So what I'm going to do is I'm going to finish this off. Okay, you can speed towards the end to see my results, but I'm going to do it again and again, just because I like the colour. Okay. First things first, and I'm going to wash this out. Now the manganate that's in here, and this as well, you don't want to throw it in the sink. Reason for that is because it is damaging to the environment. Okay, so you do not want to put it down any sinks. So, I have a nice big bucket, a glass one, and I'm just going to pour it into there now. And then I'm going to wash it out with some dim as well. Now you may, if you want to be really, really accurate, you may want to get a brand new flask. brand new dry flask, and that's fine. And then we don't be legend. Just fill it up on my distilled water. Water. I am going to get a clean flask. Stay accurate. I'm not going to top up my burette, just purely because it's only gone down to 14ish, so I've easily got another round in this. Now, of course, if yours is coming out at quite low, you may want to top it up. I don't think I'm going to be able to get. I find these much more reliable than the pens, to be honest. This is why I like to use these. I'm only going to do one more. If you want the calculations, skip ahead. Okay, so my start is going to be 13.90. Timer at the ready. I'm going to show you which clicks are up as well. Okay. So, if I'm wanting to get another 13, whatever. Calculator, 30.9. Okay, so I want to go down to roughly 25, 26. Okay. That's fine. So what we'll do is I'm going to speed down to around 26. That's 26. It will change back, don't worry. I hope. Yeah, there you go. Okay. Lovely, lovely. Okay. So from here I am going to drip, drip, drip. Drop at a time now, because I do want it to be as accurate as possible. So yeah, this does take time, as you can tell. But if we do it right, the results are worth it. Okay, so I'm up to 27. Nope. Got up to 22. The only trouble with titrations or with burettes is that if you have one that's very temperamental with the tap, you just end up adding too much. But this is not going to be our end point, so it's fine. Nearly there. A bit more careful. It's a lot of waiting around. I know where it should be roughly, so that's why I'm adding 3 drops. One more drop, I think. Oops. Oh, look at it. If you are going to do this, make sure you have a tap that's a bit more tight. Okay. Yeah, I think this is going to do it. Yep, 30, and the pink is still slightly there, so where are we? We're at 27.7. 0. Okay. So I'm just going to do some calculations with these results. Alright, so let's calculate 13.9, oops, 9 minus 0.65. So that's 13.25 change, and then 13.9 minus 27.70. Oops, wrong way. 27.70 minus 13.9. Oh, it's 13.8. Okay. So I did do an oopsie, as you saw. I did too much in at the end. However, we are going to go with this one just for our calculations, because I don't want to take up a lot of time. Well, saying that when it's nearly 50 minutes. Right, let's get on with some calculations then. So, normally we take an average. You would definitely get a couple more tries, okay, and you would get an average. Roughly you'd want 2 or 3. 3 would probably be better, and you want them in concordant with each other, which means that they are within 0.02 of each other. That's how you're going to get the most accurate calculation. Okay. So we don't know the concentration of our sample. So this is Fe. We know the volume that we've used. Okay, we know the volume that we've used because that was 25 centimetres. Yeah? We don't know the concentration of our manganate. Oops, 2. Cheers! Excuse me. I'll take these off because I'm sweating. Oh. Not a bad thing about titration. Okay. So of our manganate, we do know the volume. Our volume is from the titer. So it should be an average, but I'm just going to use 13.8, and that's centimetres. And the concentration of this particular one is 0.02 molar. Okay. And from the calculation here, we know that for every 1 mole of manganate, we have 5 moles of iron. Okay, so first we have to work out the moles of our iron. So N equals CV. So to find moles, you take your concentration and you times by the volume. The volume has to be in decimeters. So 0.02 times by 13.8 divided by 1,000. So to get from centimeters to decimeters, you have to divide by 1,000. Okay, and just for note, decimeters is the exact same as litres. Okay, so if it says moles per litre, that's fine. You're still going to have to divide by 1,000. Still going to have to divide your volume by 1,000. All right. So I know I'm not using a scientific calculator. Don't come for me. 13.8 divided by 1,000 times by 0.02. So 2.76 times by 10 to the power of minus 4. Yeah, 4. Okay, so that is moles of MnO. 4 minus. Yeah. Okay. So for every 1 mole of manganate, you have 5 moles of iron. So what we're going to need to do is take our oops, moles of Fe should be 2.76 times 10 to the power of minus 4 times by 5. 0.00138, aka 1.38 times 10 to the power of minus 3. Okay, and that's moles of Fe. Now, this here, this is the amount of moles that's reacted in our 25 milliliter sample, centimeter sample. Yeah? So now let's find the concentration, then we can find the mass. Okay, so to find concentration, it's moles divided by volume. Okay, so moles is 1.38 times by 10 to the power of minus 3 divided by 25 divided by 1,000. We still have to divide by 1,000. This is in moles. Concentration is moles per decimeter or moles per litre. Okay, so let's do that. Divide by 0.025. So now we've got concentration. We already know our moles and all that sort of stuff. That's grand. Now we can find mass. Mass in 250. Keep the same things, Lindsay. Okay. Now, this is how many moles is in 25 centimetres. When we made up our volumetric flask, we did it to 250 centimetres. Yeah? So we have to find out how many moles in total we used in our solution, our standard solution. So the way that we can do that is we do 250 divided by our sample size, so 25, times by our moles here, 1.38 times by 10 to the power of minus 3. Okay, that gives us our total moles in 250 divided by 25 times by 0.12345. Yeah. Okay. Of Fe in 250 centimetres. Okay. From there, we can turn this into mass. Okay. Mass equals Mr. mole. So the MR of Fe is 56 times by 0.0138. 0.7728 grams. Now, just comparing to the mass that we worked out before, yeah, when we transferred it over, we can see that we've lost quite a bit of mass. But as mentioned, you have a whole lot of other stuff other than iron in these iron tablets. Okay, you can find out what exactly is in your iron tablets by taking a look at the ingredients. Is it going to focus? There we go. Okay, so here it says bulking agent, which is what we could see floating about. There's maltodextrin, which helps in the breakdown of this product. Ferrous fulminate, however you want to say it. That's basically the iron. But we also have magnesium serenate. So there could have been some side reactions happening because of the magnesium, because of the maltodextrin, because of the bulking agent. So the mass that we have calculated is definitely not going to be the same as the mass that we've weighed. And that's simply because of all the other stuff inside of an iron tablet. Okay? Now, this is the mass of iron in 5 tablets. So to find the mass of 1 tablet, we have to divide by 5. No brainer. Okay. So it's 0.15456 grams of Fe in 1 tablet. Now, in our bottle, it does give it to us in milligrams. So this has 14 milligrams. Okay, to convert from grams into milligrams, you just have to divide by 100. Okay, so as you can see, this titration is not as accurate. Okay, why that could be? Probably because I only used one value, probably because I didn't do it multiple times. Okay, but either way, this is how you calculate the amount of mass in 1 tablet. Okay, if you're wanting just to find the concentration, you do this step. If you're wanting to find the mass, you'll have to do this step. So this one here is optional. Okay, and there you have it. That's how you calculate the amount of iron in an iron tablet. Obviously, not accurately. Let me know if you have any questions in the comments below. If you're stuck on anything or anything like that, again, drop a comment, give this video a like, subscribe. I'll be giving a lot more chemistry content over this next year. Okay, toodaloo.